In this video, we're going to be solving the tutorial questions on pages 37 and 38 of the course notes. So this is question 1, and we're presented with a circuit that has resistors in parallel. We're asked to find the total resistance of the circuit and the circuit current. This notation of 4K7 and 3K3, this means that the resistance of this first resistor is equal to 4,700 ohms, and the second resistor is equal to 3,300 ohms. The K stands for kilo, which is 1,000, so that's 4,700 ohms. So that's what that shorthand is for. And well, you'll sometimes see things like that in the course notes and tutorial problems. We will not be using anything like that in the assessment. We'll always clearly state what a resistance is. So in part A, we're asked to find the total resistance of this circuit. Well, we have a formula for the total resistance of a parallel circuit with two branches, and it's this: the total resistance is equal to resistance 1 times resistance 2 over the sum of those two, R1 plus R2. And so we can put in our numbers. So we have, well, we'll call the top one, you can be number 1, you can be number 2. So we'll have 4,700 plus 3,003 times 3,300 divided by 4,700 plus 3,300. Now, hopefully you can see the bottom. We're going to get a nice number of 8,000, but we need to work out what the top is in the calculator. Unless you're good with your mental arithmetic. It's something pretty big. It's 1551000. Of course, there's nothing at all to stop you putting all of this into the calculator in one go. You might want to break it down like I'm doing, like this first of all. So we divide this number on the top, which is 15,510,000 divided by 8,000. And we get this answer here, which is 1938.75 ohms, which we can see from the question is indeed the correct answer. So we're happy with that. And then in part B, we're asked to find the circuit current. So again, we're using Ohm's law here. And to find the circuit current, we can use the version of Ohm's law where we have the supply voltage equal to circuit current times total resistance. The circuit current is equal to our supply voltage divided by total resistance. That's going to be 9 volts divided by this number we just found in the previous part, 1938.75. And putting that into our calculator, we're going to get something that looks like this: 0.00046 amps. And so we of course want to convert that into milliamps. It's a more convenient unit to work with. We don't have all these zeros. We can write that as 4.6 milliamps. So we just multiply by 1,000 to make that conversion. And so that's question 1 from the parallel circuit tutorial. So we'll move on to question 2. And I should have said at the start of this, if you're looking for a particular question, just skip ahead. They're all just done in order. I'm sure you'll find it if you just skip through the video. This is question 2. Find the total resistance of the circuit current, and then we want to find the current flowing through the two individual resistors. So this is quite similar to our second worked example. If you've watched that video, that might be helpful as well. So total resistance in the circuit, again, our formula is going to be this. I'll label our two resistors just so that we can refer to one as 1 and one as 2. And as I've said in the series circuit video, it does not matter which order you label these in. They're completely interchangeable. It's just so that I have something to point to when I'm saying I'm talking about resistor 1. In fact, actually, it does tell us in the question, it doesn't tell us in part C. It says resistor 1 is the one that's got a 10 ohm resistance. So I've actually labeled them the correct way. But the first two parts will still have worked no matter what I called them. So let's put in our values. That means we've got 10 times 24 divided by 10 plus 24. These are coming from the values of the resistors given in the question. We have 240 divided by 34, and that's going to be equal to 7. I don't think it's exactly 7, I think. 7.05 in this number, so pretty close to 7, safe enough to round it to. So we have 7 ohms here for our total resistance. Now we need to find the circuit current, and again this is quite like what we did in question 1. We can use Ohm's law again to find the circuit current based on the supply voltage and total resistance. I'm just rearranging our formula once again, and we put in our numbers here. So we have 110 volts divided by 7 ohms, and when we put that into our calculator, we're going to get an answer of 15.7 amps. So far, so good. Now we're asked in part C to find the current flowing through resistor 1. So resistor 1, we know has a resistance of 10 ohms. We're told that in the question. To find the voltage across it, well, we look back to what we know about parallel circuits, and the voltage through each branch is the same to the voltage they're connected in parallel to. So each of these resistors is connected in parallel to the supply voltage. So the voltage across resistor 1 is going to be 110 volts. And that's also the voltage across resistor 2. That's how parallel circuits work. But what's not true is the current at every point being the same. We don't know that. So this current is not 15.7 amps. That current gets split between resistors 1 and 2. So we have to work that out. And again, voltage and resistance, we're using Ohm's law once again. I1 is equal to V1 divided by R1. So we have 110 divided by 10, which gives us 11 amps as the current across resistor 1 flowing through it. In part D, we could use the exact same method if we wanted to, and we could just do I2 is equal to V2 over R2. We know V2 is the same as V1, it's 110 volts, and R2 is 24 ohms. Or we can also use Kirchhoff's first law, which tells us the circuit current is going to be equal to the sum of the current in each branch. Our total circuit current was 15.7. We've just worked out that the current in branch 1, where resistor 1 is 11. So that leaves I2 being 15.7 minus 11, so is equal to 4.7 amps. And you'll notice that this is in fact different to what we have in the question over here. And there's a reason for that. It's not a scientific reason. It's nothing to do with any electronics. It's just a matter of rounding. We've taken that from our total current, but it's dependent upon rounding. If we had done the method I described before, taking I2 is equal to V2 over R2, we would have 110 divided by 24, and that would give us an answer of 4.58 amps. And you might think these two answers look quite different to each other, but it's because of rounding they're the same. And probably I've gone with this to try and keep things right for the answers in the question, but probably if we had had an answer here, something like 7.05, let's just see what it was. 7.059 ohms, and use that throughout the question. When we got to part D, these two methods would marry up a bit more. So if you get an answer that's not quite close to the answer in the course notes, don't worry too much. But you can always check. I'm always happy to have a look at a problem like that, but that's why sometimes you're going to see slightly different answers coming up. However, having got to this point, either of these I would accept as the correct answer, so don't worry. If you have got an answer that's slightly different, there's a possibility that that's the reason. But in order to avoid that, generally we'll keep things to more than just a whole number. So a few decimal places certainly helps keep things right. So you could have, you'd go away 7.06 would have been a good way to round that to, just to make sure we have enough accuracy there as well. But or 3 decimal places is fine. But as I said, if we'd got that answer for D, it wouldn't be a big issue. So let's move on and look at the next question. The next question is question 3, and we're going to take a look at this circuit here. So we're asked to we're asked to find again the total resistance, the circuit current, the current flowing through each resistor, and then to check using Kirchhoff's law that these things add together. So that the answers that we get in part C and D are indeed equal to the total current in the circuit, and it should be pretty clear by that point they are, but we'll confirm it at the end of the question. So part A, total resistance in the circuit. This question does tell us which one's which, so this is 1 and this is 2 here. So I'm going to put these in that order. 660 times 470 divided by 660 plus 470, and that's equal to 310200 on top and 1130 on the bottom. So that gives us an answer of 274.5 ohms for our total resistance. In part B, we're going to find the circuit current by dividing the supply voltage by the total resistance that we've just worked out. That's 240 volts divided by 274.5. So it's going to be a bit less than 1 here, we're going to have here. So 240 divided by 274.5 gives us 0.874. And of course, our units are important, so we have amps there as well. In part C, we're asked to find the current flowing through R1. Well, R1 has a resistance of 660 ohms. The voltage in R1 is 240 volts. So we can find the current by dividing that voltage by that resistance. 240 divided by 660. And for that we get, it gives it a very accurate 4 decimal places in the question. So we'll stick with that. 3 decimal places would normally be more than enough, but let's keep with what the question gives. 0.3636. That's actually 3636 all the way, just recurs 3 sixes amps. And in part D, we're asked to do the same thing for resistor 2. Well, we know resistor 2 has a resistance of 470 ohms, we're told that in the question. Each branch has the same voltage as the supply here, 240 volts. So we can use our Ohm's law again to find the current, V1 divided by V2. Well, it doesn't matter because V is the same, but V2 divided by R2 is equal to 240 divided by 470. Again, the course notes gives this to 4 decimal places, so we'll give our answer the same and check it matches up. And we get 0.5106 amps to 4 decimal places. And that is indeed what the course notes has. So we've done parts A, B, and C. Then it wants us to use Kirchhoff's second law. I think sometimes the course notes gets Kirchhoff's laws mixed up a little bit, or maybe I do, because I thought Kirchhoff's first law was about, yes, I am correct. I just double checked that. Kirchhoff's first law, so it says Kirchhoff's second law is the one about voltages in series circuits. Kirchhoff's first law is the one that says the circuit current splits up between branches. I suppose it doesn't matter. You don't even need to remember Kirchhoff's name. It's just you remember that the rule for parallel circuits is this, that the circuit current is going to be equal to the sum of the currents in each branch. And we want to check that these two things are equal. So we worked out IC in part B, and that was 0.874, and we've worked out I1 and I2, so let's add them together. We get 0.3636 plus 0.5106, so add these together. We should put amps in that as well. units are always important. And that gives us an answer of 0.874 amps, 3 decimal places. So yes, these two things are the same. So Kirchhoff's first law does hold here, and we've checked that out. And in a question like this, like we looked at in a previous example, this is an alternative way. If we had already worked out the circuit current in one of the branches, we could have used Kirchhoff's first law to find the other branch. But we can also do it the way we've done it here as well. Both are equally valid. So let's look at the next question, which is question 4. And similar to what happened in the exercises for series circuits, the course notes gives us a taste of what it is when we don't have a diagram, but we can make one ourselves if we feel we need one. I'll be making one either case here. So we've got a 6 ohm resistor and a 75 ohm resistor connected in parallel across a voltage supply of 12 volts. We're asked to find the circuit current. So this is what our circuit looks like. We've got 2 resistors that are in parallel, and they're connected to a supply voltage. We're given values for all of these. So our supply voltage is 12 volts. We have a 6 ohm resistor and a 75 ohm resistor, and we're asked to find the circuit current. Now, having done the previous examples, you probably remember that in each case when we found the circuit current, we found it by taking our supply voltage and dividing it by the total resistance. But you know, we don't have the total resistance yet, although we do have the supply voltage, it's 12. So we're going to begin by finding the total resistance. We do this exactly as we were prompted to in every other question, using the values of our 2 resistors that we have here. So we can put this in. We're going to have 6 times 75 on the top and 6 plus 75 on the bottom. So we're going to have 450 divided by 81. That's not something that I can do quickly or possibly at all in my head. So let's work it out. And it gives us 5.55555 and so on. Just 5s all the way after that. So we say 5.556. We'll round it to 3 decimal places, and that is ohms. And you'll notice this is quite close to the value of our smaller resistor, and as we've seen before, it's smaller than both of these resistances. That's what happens when we add resistors in parallel. So we now have the information we need to find the circuit current. The supply voltage is 12 volts, the total resistance, 3 decimal places, 5.556, and that's certainly accurate enough to carry out this calculation. So putting this into our calculator, we do indeed to 2 decimal places, the circuit current is 2.16 amps, as we can see indicated in brackets after the question there. So what's different about this question is we're not given a diagram, and we could have worked it out without it, but we need to remember, even when we're not prompted to carry out that step, that we have to find out the total resistance of the circuit first of all, before we can calculate the current in the circuit. So let's look at the final question from this set of tutorial questions now. So question 5. A 440 ohm resistor is connected in parallel with a 330 ohm resistor. The current through the 440 ohm resistor is 300 milliamps. Find the current through the 330 ohm resistor. Okay, this is something that we've not seen before, and I do think drawing a diagram here is going to help us work things out. So let's have a look then. Our circuit's going to look like this. We're going to have 2 resistors and supply voltage connected in parallel. And we have a resistance. As this one, I'll just say you're the 440 ohm resistor. It doesn't matter which way we connect them up. The circuit will behave the same either way. It's 330 ohm. And the current, just take a wee ammeter on here to show us what's going on. We've got a 300 milliamp current a wee ammeter there just telling me what's going on in that part of the circuit. The 300 milliamp current running through the 400 resistor, but we know there's nothing to say. In fact, it's probably strong to suggest it's not going to be the same as the current in the other branch. It's definitely not the same as the circuit current because that splits off to give these two currents. So we'll label these 1 and 2, and let's have a think about what we can find out. So we want to find out the circuit current. So we want to find out what I2 is. So we know I1. I1 is 300 milliamps. Maybe write this as 0.3 amps because that's what the units we're going to be working with. We know our resistances, but we don't know anything about this second resistor's current. But what we do know is that the voltage through both resistors is going to be the same. So we can find the voltage through resistor 1, and that will be the same as the voltage through resistor 2. Since we know I1 and we know R1, which is 440 ohms, we can find V1. V1 is equal to I1 times R1. And so this might not have immediately occurred to you. Sometimes got to just play about with the set of what we know. And if we ever are given a component and we know two things about it, and whether it's a series or parallel circuit, we know the resistance and the current running through it, or we knew the voltage and the current, or the voltage and resistance, we can use the two things we have to find the third. And so we do know this for this resistor 1 here. So our current is 0.3 amps. Our resistance is 440 ohms. So this allows us to find the voltage of our circuit, which is about 132, but I'm not confident enough to just write that down without checking it. But thankfully it is the right answer, 132 volts. But this means that for our second resistor, we have V2, or V2 is equal to V1. The voltage in every branch is the same as equal to V supply. We can actually write down here our supply voltage is 132 volts because it's the same in every branch. But importantly, V2 is equal to 132 volts. R2, we're given the question, is 330 ohms. So this allows us to find the current in this resistor, the current I2, which we don't know. I2 is equal to V2 over R2, which is 132 divided by 330. And putting that into our calculator, we're hoping it's going to pop out an answer of 0.4, and indeed it does, 0.4 amps. So you might want to pause and think about this question. It's not quite like the others. We had to do a little bit of thinking about where to start getting information. But the thing that helped us out here was, first of all, we could use Ohm's law to find out the voltage in the first resistor. And we could have done that in any problem if we knew a current and resistance. But the thing that really helps is finding that voltage and knowing the voltage is the same in every branch gives us the voltage in the second branch. And because we've got a voltage and a resistance, we can use Ohm's law again and get that current. And that concludes the final problem from the parallel circuit tutorial questions. As I said in the case of the series video, you may still will have questions after that. You can get in touch with me either by email or speak to me the next time we're in class together. But hopefully these videos have been helpful in understanding how to reach the solutions in these problems.